Hello everyone. In this video I'm going to go over electron level diagrams and electron configuration. Now you would have hopefully have gone over quantum numbers and done a bit of practice with that. If you haven't yet, probably best to start there. All right, we'll review a bit as we begin here. Okay, so let's start. So to review your quantum numbers, a few of them, at least the first few, here is a periodic table. And some of these electron configurations for each of the elements are already written. So here we see, let me switch my pens. Okay, so our S block is here, our D block is here, our P block is here. Notice that our F block is at the bottom. We'll get to those in a bit. But our principal quantum number, 1 in this case, um, refers to hydrogen and helium. Moving on, reading from left to right, going from top to bottom. Our secondary quantum number is 2, all along this row. And here we have the S orbital and we have our P orbitals. And within this S orbital, there's 1 electron. There are 2 electrons here. And then moving on to the p orbitals, we have 2p1, 2p2, just continuing to add one more electron. Right. Another representation is here. Right. So all of the 1s's are along here, 2s's are along here, 2p's are along here, and then you go to the next row, 3. One thing I wanted to point out, we'll get to it right now. It's after 3s, then along the third row comes 3p. Now you continue the pattern, and it's 4s, and this is a question in our class yesterday or earlier today. On the third energy level, it looks like we only have the s orbital and the p orbitals. Now, there actually is another one. Within this third energy level, where n is equal to 3, we have, so where n is equal to 3, we have shapes that range, and our orbitals are, right, they range from 0 to n minus 1. It's 0, 1, and 2, which represents S, P, and D. And as you look along the third row, you might wonder, you don't really see D, you see S and P. But look here, 3 Ds right there, right? But since the periodic table is organized by atomic number, it wouldn't make sense that these transition elements are all moved up one. Instead, we know that after 4s actually comes 3D, right? Okay, so we'll talk about these certain electron configuration rules and quantum number rules in a bit, but just to break down how we're going to write it. So this is hydrogen's electron configuration. Think of it as the address for an electron. It just means that when n is equal to 1, in other words, our energy level is shown here as a coefficient. And S refers to the suborbital shape. In other words, the L number is the secondary quantum number. S, right? 1 as a superscript refers to the number of electrons within that suborbital, which is within that energy level. Oops. Let's move on. Okay, so these are the rules. I'll keep on writing. Let me erase. These are the rules then to write these electron configurations and to think about expressing quantum numbers. Your Aufbau principle just tells you that you have to place electrons in the lowest possible energy first. So you're not, so lowest possible energy, so lowest energy level available. So as you begin to write, and it'll make more sense when you start writing these electron configurations, but as you begin to write, you don't place an electron on a 3p energy level when the 1s has yet to be filled, right? Kind of intuitive, but it's worth mentioning. Hund's rule says that you have to place electrons singly. So go back to highlighter. All right, so place electrons singly before you begin to pair. Oops, I'm not looking in the right spot. Place them singly before you begin to pair them up. So I'd like to use the car parking lot analogy. So you don't want to park, if you're driving, you're going to park your car. You don't want to park your car right next to another car if there's plenty of space available elsewhere. You want to park further away, or you want to park at least one spot away from someone else. So you only begin to pair electrons up once there's no more else to go, once there's no more room. And we'll get to how that looks like, but it's especially relevant for the p orbitals. Right, and we'll get to examples. The Pauli exclusion principle we talked about in our last lesson. So elements, rather electrons, can't have the same quantum numbers, right? So all 4 quantum numbers have to be different for every electron in an atom. Okay. Now, we're going to start to fill in or write these quantum numbers. We already talked about this last point here, the fact that 3D is actually lower than 4s, and that there's a certain order to write. And there are these pictures you can refer to help you decide how to write these electron configurations, but I usually just like to stick with the periodic table. So I think I have a good periodic table opened up here, right there, right? Just try to stick with following left to right, reading top to bottom. So 1s, 1s, this is 1s1, this is 1s2, so on. 2s, 2s is here, so this is 2s1, 2s2. Continue reading left to right. It will create a pattern that looks like this. So 1s and then your 2s following these arrows, 2p, 3s, right? Another example here, you just connect your arrow to the end of the next one. All right. Now these are like other slides you've seen in the past. These are instructions on how to write electron configurations. Probably best for me to not read all of this to you. You can read this yourself. I'll just scroll this down. I'll take points out of this so you can see, but it will help if we start to do some examples. So first, figure out how many electrons there are. Arrange. You can start writing your suborbitals and then fill in electrons afterwards. That's one way. You're going to see that I'm going to do it slightly differently, but these are just general instructions you can follow and it'll work well. One thing I want to point out that if you add all of the superscripts, so the 2, 2, 6, 2, and so on, they should all equal the total number of electrons that that element has. Let's do some examples. Read over this, practice. If you need to, use this as a guide, but let's get to some practice. So here's a question. What element has this electron? You can see the timers popped up here. Normally that would have meant your turn in class to practice. So if you'd like to pause the video and try to answer these two questions, it's probably a good idea. So what element has this electron configuration? Next question is a bit of a trick question here, but hopefully you can figure it out. What is the electron configuration for Z is equal to, that just means atomic number, Z is equal to 36, or for krypton. Okay, so feel free to pause. All right, well, hopefully you've paused and you try to figure this out. 1s2, 2s1. That means the last electron in this element is a 2s1 electron. Going to our periodic table here, we're on the second energy level, we're on the s block. 2s1 means lithium, right? Lithium has that one electron in the 2s orbital. So let's see if that's right. Lithium. Right. Now, krypton, let's find krypton in our periodic table. Krypton is a noble gas right here. Now, it is along the 1, 2, 3, 4th energy level. Okay, so we know that everything else before potassium, so argon and above, are all filled. We have the 3s2, we have the 3p's over here, they're all filled. We have the 4s filled. Remember, this is the trick to it. We go 4s, and as you read left to right, it's not 4d, right? 4d is one below. It's actually 3D. So all of the 10 electrons in the 3D orbital, suborbital, are all filled, right? So after 4s2, we get 3d10. Then we start filling in all of the 4p electrons. So let's go back to that. So go through this slowly. Your first energy level is completely filled. Of course, it's only two elements there, hydrogen and helium. Your second energy level begins with S, and that's filled as well. Your second energy level, P orbital, is all filled as well. Third energy level is all filled as well, your S and your P. Now, finally, we're down to our fourth energy level, and the 4s2 is filled, right? 4s2 is right here. These two are filled. Then we get into the 3d orbital, and that's all full as well. So 3d10 is all filled. Then we get to the 4p, our last suborbital, and we see that it is completely filled too. It is a noble gas, so we see that it's completely filled. Right? So that is the electron configuration for krypton, element 36. Okay, let's hide this for next time. I think I moved that too. I'll fix that later. Okay, now you can probably appreciate that this might take a little while to write, and that's only for element 36. And if you're asked to continue along the periodic table, it would get pretty long and maybe tedious to write every suborbital. So an allowed noble gas core electron configuration, or a condensed version, can be written. And all you do here is you just take the preceding noble gas, right? So the noble gas that came before it. For example, if you're writing the electron configuration for calcium, the noble gas that came before it is going to be argon. So you'd write argon in square brackets and then write only the valence electrons or the outer electrons following that. It really cuts back on the amount of time and space you need to write these. So let's see. Noble gas core configuration for sodium. Okay, let's see where sodium is. Sodium right here, third energy level. Neon was the last noble gas, so you write neon in square brackets. Look, we've done that, neon in square brackets right here. Then we write 3s1 because sodium has 3s orbital, 1 electron, 3s1. So that's a shortened, condensed version of that. Okay, another opportunity for you to practice here. We're going to do write the condensed electron configuration for aluminum, atomic number 13. So aluminum is right here. Okay, want to take a minute, pause the video, and try doing it yourself. Okay, well, hopefully you've paused it and give it a try. Find where aluminum is. We did before. Aluminum is right here. Its previous noble gas is neon, so you write neon in square brackets. Let's see if we've done that. Okay, so neon in square brackets. Then after neon, we have 3 more electrons to fill in. We have the 3s2 is completely filled, and then the 3p isn't completely filled. There is only 1 electron here, so it'll look like this. Neon in square brackets, 3s2, 3p1, and this is the condensed version. Instead of writing all of this, it's sufficient to write this. Now the question here is, will I ask you to write it in one way or the other in any task or evaluation you have? If I don't specify, if I don't ask specifically to write it in a certain way, you can always opt for writing it in the condensed form. I'll be clear though. Okay, next, energy level diagrams. You'll often see energy level diagrams written or drawn like this. At least they start off this way. I'm going to draw it a bit differently for you, and you're going to see why. So they are essentially arranged, electrons are arranged in a similar way as electron configurations are, but they're arranged in a way that show the relative distance away from two things, away from the nucleus, which is at the very end over here, and away from each other. Now, the further up the periodic table you go, the more convoluted this gets, and the more overlap there tends to be. But what's important in grade 12 that wasn't so much in grade 11 is this distinction here. Between the first energy level and the second energy level, the distance is actually noticeable, right? So this distance here, right, it's much greater than the distance between the 2s and the next 3s. And those distances continue to decrease. 3 and 4 is even smaller. 4 and 5 is even smaller. Right. Now, you don't have to worry about those. Just make sure that when you are drawing this, the first and second energy levels do have a notable difference. Okay. So you might see this online, and it's not wrong. Do whatever your teacher or professor asks you to do. This follows the order of that the periodic table is read in, left to right, top to bottom. I like to draw it a bit differently and found in some textbooks as well. So I'm using this as a point of reference, but I'm going to draw it a bit differently. So I'm going to minimize, I'm going to make this a bit smaller, and I'm going to redraw this. Hopefully it's not going to be too messy. Let's start off with an arrow. So arrow always pointing up, right? You'll want to write E, right? E for energy level diagram. Then we begin at the very bottom. So this is correct. We begin at the very bottom. I'm going to undo that. That doesn't look good. Okay, so that's 1s. Then 2s. You might want to leave some more space. Okay, now 2s is then we have to remember that in the second energy level, we have not just the s orbital, but we also have the p orbitals, and they are slightly higher in energy, so they should be written slightly higher up and off to the right. And we know that there are 3 suborbitals within the p block. So we have 2 p x, 2 p y, and 2 p z. Okay, then we continue. 3s is up here, right? Then again, we have 1, 2, 3, 3px, 3py, 3pz. So far, it looks exactly the same. Okay, now we get into the s orbital. So your s orbital is higher up. I'm just giving myself some space here for s, right? Okay. Now, as you read the periodic table, going back here, we're here. We've done 3s, we've done 3p, now we're at 4s, right? Now we have to go to 3d. Now, 3d isn't higher up than 4s. Its energy level, and we're after all drawing energy level diagrams, so its energy is actually less than 4s. So instead of writing it like it is here above 4s, we're not going to do that. We're going to stick within the realm of the third energy level, right? If n is equal to 3, then the energy is using the equation. Let's see if I remember it. Energy is equal to Planck's constant, Planck's equation. That's it, right? Is proportional at least, right? Energy proportional to the n value or the value of the principal quantum number, then 3 is less than 4. So 3 shouldn't be above 4 is the way that I see it. So let's write that along to the right here. So 1, 2, 3, 4, 5. And then there are different orientations or third quantum number here, but we're not going to focus on that. I'm just going to call this the 3D. Okay, we're not going to get as specific and start to label our orientation. So 3D is just written here, right? And then we continue using the periodic table as our guide. So 3D, then it's 4p. Lined up here, we write 4p. 1, 2, 3, 4px, 4py, and 4pz. Right, and you continue. The highest it will ever go, so that you know, is 7s2. Okay, so we will do to some degree, a little bit less in any kind of a e-learning or distance type of class, but we do normally go over the first row of the F block. We'll talk about that in just a bit. Okay, so titanium. Titanium is this 22nd element, so it's 4s2 and then 3d2. So let's start filling in electrons, and all you do to fill in electrons are use arrows. Now they have to be, you're following the three rules, right? Hund's rule, Pauli's exclusion principle, Aufbau principle. So you begin at the bottom, spin up, spin down. That's 2 electrons. We need 22. Spin up, spin down. Now watch how I fill this in. Spin up, spin up, spin up, right? Don't park next to a car if there's space. Now that there's no more space, now you have to park next to a car. Then we go spin down, spin down, spin down. Okay, continue, spin up, spin down. Make sure we know what we're doing here. So we're at the 3p energy level or suborbital. 3p is right here. So we still have a little bit to go. And to fill up all of 3p, 4s, I'm going to pause after 4s. All right, so make sure we're doing this right. I'm going to pause after here. So up, 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 down, down, down. Right, then not going to go off to 3D just yet. We're at 4s. So up and down. Okay, in the third energy level, we have 2 electrons. Oh, it looks like this. 1 up and 1 up, and we stop. And that's the energy level diagram for titanium. Right, again, we'll continue to answer more questions, go over more examples when we meet. Okay, further down the periodic table, this is I pulled this quotation from this review. Right? I don't like to make things up or necessarily believe what I read in a textbook if I think there might be more information to it. So I looked up a good review on electron configurations for elements lower in the periodic table along the F block. And this is what I've surmised. And this is my reference, so you know where I'm looking. Okay. This can get a bit confusing. For our distance learning purposes, so if we're not in class constantly, you will not need to know these. I do want to briefly explain them though. Some of these you will end up having to memorize because there isn't too much, well, there is a pattern, but for some it just doesn't apply. So when we're in class, barium, pretty simple. Barium is right here. So normal patterns apply. It's when the f block begins that it gets a bit funny. Now our d orbital continues at that point. So after barium, we have our first d electron. Okay, this is all written in condensed form, otherwise it would just be really long. So lanthanum begins, we get 5d1. It follows the same rules. We know that d is always one energy level below. Next, okay, we have cerium. We had lanthanum, then cerium. Cerium, this is the electron configuration for cerium. That's where our F block begins, but only for a moment, you'll see. So 6s2, now F goes before that, right? And we still have that one d electron. Now, to add to that confusion, this electron from d is borrowed, moved off into the f orbital, and d disappears momentarily. So this d electron now becomes part of, I think it's praseodymium. Let's see, don't often work with that one. Praseodymium, very good. So this d electron is now incorporated into the f block, and we still have 6s2, but now we have so 2 levels before, so it's 4f. Lanthanum, cerium, and praseodymium now have a filled 3 electrons. 3 electrons. Fortunately, though, that pattern does continue until you reach the end of your F block. So when we're at, I think this is ytterbium, YB, ytterbium, not ytterbium, ytterbium. So ytterbium is almost done. We're almost at the end of our F block here. So this is F14, but our F block can only hold 14 electrons. So how is it that we still have lutetium at the very end here? We can't have 15 electrons. But remember, we borrowed that one d electron. Now that d electron comes back, and it goes back to where it came from originally. And this is what happens. That shows up again. See how these has now reappeared? That now accounts for all electrons. Then the pattern continues as it normally did. Okay, distance learning, e-learning, we won't need to know this. Okay, this you will have to know there are some anomalous electron configurations, but there's a pattern here, not difficult to figure out. So it is electronically more stable if we have an electron configuration where we see a D4 or, well, I'll get to those ones. Wherever you see, get a highlighter, wherever you see D4, so a d orbital that is almost half filled, so 1, 2, 3, 4. So chromium down, wherever you see a d4, what's going to happen is an electron from the previous 4s, or s, 4s in this case, but generally the previous s electron is going to be borrowed so that you can get a completely half-filled d orbital and a half-filled s orbital, which is more stable, more energetically favorable than it is to have a full s orbital and only 4 electrons in the d orbital. So s2d4 becomes s1d5. Something similar happens whenever you have this sort of configuration. So whenever it ends with a d9, really close to having completely filled the d orbital, it's more electronically favorable, more energetically favorable, I should say, to have this one of these electrons from the s2 bumped into the d. So now we have s1 d10. So chromium would be incorrect to write this way, and it would be correct to write that way. Okay, for the purposes of this course, and especially as we're doing this online or distance learning, we will not go past S2. Actually, let me change that. You will not see the F block at all. Okay, so if we're not in class constantly, I might make reference to the F block and what that means. You certainly will need to know its quantum number and how to write those, but we will not go for distance learning past. See, F block begins here. We're not going to go past barium. We'll stop right here. Okay, we'll do what you did in grade 11. In grade 11, you stopped at barium. That's where we're going to stop for energy level diagrams and for electron configurations. This is a list of other predicted configurations and actual configurations. It does get a bit messier. You will not need to know these. I've just highlighted or put boxes around the ones that follow that anomalous configuration where you borrow one electron and move it into your d orbital. that is it. Okay. Um, just some extra notes here. Of course, you never get homework, you get home fun. So textbook is great with this section. Practice these questions in your textbook. We'll meet online if you have any questions. See you next time.